Hi everyone, thanks for coming. This week we're really excited to host Professor Davide Gerosa from the University of Milano-Bicocca. His research focuses on relativistic astrophysics, black hole binary formation, post-Newtonian dynamics, and gravitational wave astronomy. Promises to be a really exciting talk, so over to you.
Thanks a lot for the invitation. It was really lovely to get a student invitation, not an academic. Well, it is an academic invitation, but directly from the student is particularly nice, if I can say. So yeah, my name is Davide. I'm over in Milan, northern Italy, where I lead a group in gravitational wave astronomy. So hopefully today will be an introduction or so to the beautiful world of black holes and gravitational waves. So let's see how far we go. All right. So I want to start from quite far back and ask, okay, what do we know about the universe? Very general question, but the answer is a lot. And if you think about it, really, I mean, we got to know the universe in the, hundreds of years of astronomy, from the small scales of, well, planets, I guess we live on one, to the stars that we see in the sky. These guys are part of galaxies, like, 10 to the 11 stars in each of the same. And each of these dots in the deepest images that we take, each of these tiny things is a galaxy with 10 to the 11 stars, right? So we got from the smallest scales where we live to the scales of the entire universe, right? So just thinking that we kind of know the universe from all these different scales is already mind-blowing to me. But if you think about it for a moment, of all this beautiful world, what do we actually see? Only one thing, that is light. So all that we know, it's because photons were emitted. So light was emitted, years and years and millions of years ago, or whatever, and eventually reaches your eyes when you look at the stars, your telescope. They just told me about your beautiful observing, nights that you have here with the society. So you only see light, but light is not really, so this beautiful universe does not stay together because of light. Light is like a byproduct. What keeps the universe together is gravity, really, right? So we are in a kind of bizarre situation in astronomy where the things that keep the universe together, it's one thing, but then the things that you see about the universe is another thing. It's like seeing a byproduct, if that makes sense. So an analogy would be, imagine seeing, there's an orchestra playing, but you're watching a YouTube video of an orchestra playing or a rock band or whatever, but the video is mute, right? So you see the orchestra playing, they know they're playing music, so you see them, but the actual thing that they're doing, meaning the music, you don't have access to it. Does it make sense what I'm saying? So the universe stays together because of gravity, but we see a byproduct of it, right? So the promise of doing astronomy with gravitational waves is actually to use gravity directly instead of relying on a byproduct to let me do this, to use gravity to actually know the universe. And the messengers of gravity are gravitational waves, and that's where we are going. So much like, let's try to make an analogy here, much like, some of you are, how many are physicists here? How many physicists? Oh, okay, so I can, so in electromagnetism, for the physicists in the audience, when you move charges around, you emit radiation, electromagnetic radiation, namely light. In gravity, there's an analogous effect that when you move mass around, you're actually perturbing, you're actually sending some information away under the form of gravitational waves. Now, as we will see in a minute, these gravitational waves are incredibly weak, so they're incredibly hard to detect. Let me try to make another example to kind of let you think that these things are real. Suppose that Kepler's law, I guess, right? So the period of the Earth, 1 year, is set by, among the other things, the mass of the sun, right? So Gm equal omega squared r cubed, whatever, right? Kepler's law. Now, imagine now that the mass of the sun would double instantly, or say half. Half of the sun explodes and whatever, right? Now, in order to respect Kepler's law, if the mass of the sun doubles, the Earth should go faster, should start moving faster, right? But who's going to tell us, hey, you should speed up, right? So what's the information that comes from the sun that has just decreased its mass all the way to the Earth telling me, hey, Earth, it's time to speed up now, otherwise Kepler's law is broken, right? So these information, transfer of information in gravity, it's gravitational waves, right? No, the theoretical foundation relies on Einstein's theory of relativity that predicts that the space-time itself is the medium on which gravitational waves propagate. So from an astronomer, but I'm an astronomer, so from an astronomy perspective, how many astronomers in the audience? More physicists than astronomers. Okay, okay, good, good. This is a bit annoying. Right. So from an astronomy perspective, gravitational waves then, if you can observe them, and we get there in a minute, they become a different way to understanding the universe. So here is the Andromeda galaxy in some arc. What can I do? Any Zoom grandmasters in the audience that can help me? What if I make it? What do I do? Okay, I'll try again. So this is the Andromeda galaxy in different bands of the electromagnetic spectrum here. And as you see, it's completely different. I mean, in the radio, in the infrared, you see the small stars that form these structures here. In the, say, ultraviolet, you only see the young stars. Those are the ones that live for shorter. In X-ray, you only see accreting objects that emit very high energy radiation. So even just a galaxy, if observed in different bands of the electromagnetic spectrum, looks completely different. I mean, it looks from here to there. It looks like another object, right? So gravitational waves are, well, it's really unfair to put them here. They're not just another band of the electromagnetic spectrum. It's like another spectrum, right? It's like another messenger, another way of going after understanding the universe. So it's fundamentally a new way. And historically, every time we open a new band of the electromagnetic spectrum, new and unexpected things came out. So X-ray binaries, when they first started looking at in the X-ray, gamma ray bursts, the CMB, pulsars, you know, every time they opened something new, really something that we had no clue existed before started popping out. So that's kind of the promise of now doing gravitational waves, doing astronomy with the messengers of gravity directly. So let's try to, so this is for maybe for the physicists in the audience, but bear with me. Let's try to do an analogy between light and gravity. So the electromagnetic radiation is sourced by charged particles, mainly electrons, and crucially, light is strongly coupled to matter, including our eyes. So we see in light, right? Including our telescopes or whatever, right? So that's good and bad. It's good because it's easy to detect. You know, we are a light detector ourselves. It's bad because if you then look at the universe, anything that gets between you and the source of emission might interfere and absorb some light. So gravitational waves, on the other hand, are not generated by charges, are generated by mass itself. And crucially, it's extremely weakly coupled to matter, meaning that we are crossed by gravitational waves all the time, right? But it just goes through without interacting with almost anything, such that even detecting it with our detector is incredibly hard. So that's bad because it's very hard to detect, and we need multi-million-dollar machines, like we will see in a minute. But it's also great for astronomy because it means that gravitational waves travel completely unaffected throughout the universe. So when there's a source of gravitational waves, whatever it's in between, who cares? It just goes through all the way to our detectors. That means that an observation in gravitational waves gives you absolutely pristine information on the source itself. So hope you see where I'm going. So here is going to be the outline of what I'll try to say today about this beautiful adventure of doing astronomy with gravitational waves. I'll go through the beginning and how things were actually discovered, how we use this to do astronomy, namely, figuring out how black holes are formed and how they remember, and then we go into what we actually observe and maybe what's going to happen tomorrow. That's next frontiers. All right, the beginning. So we need some equations here. So the foundation of gravitational waves, as I was saying, relied on Einstein's theory of general relativity. Some of you have seen it, some of you will see it, but the key equation is something written like this, which says that on this side is the space-time, on this side is the content of the space, namely matter and energy. And these things are intimately related, right? So the nature of the space-time is determined by what's inside, and vice versa, what's inside moves into the space-time itself. So this coupling here is what causes gravitational waves. Now, you work out some equations, but the key picture that you should have in mind, phenomenologically, is the following. So what gravitational waves do, they distort the space-time. So if you have a ring of masses, so imagine having a perfect ring of masses, and gravitational waves hitting the board like this ring of masses will deform in this characteristic fashion with two directions. So unlike electromagnetism, where charges can oscillate with one direction, that's a dipole, gravitational waves are sensitive to quadrupole, meaning two preferential directions in the oscillation. Right, so let's try to do some order of magnitude calculations. Right, so let's look at this equation. So the key quantity that we care about is h, which is the strain, mainly how what's the fractional displacement in the spacetime, which you can relate it to, well, just by orders of magnitude to something like this. So if I have a detector of size L and I want to measure a strain h, I need to measure the size of my detector with the precision delta L. All right, otherwise I'll never. So if my spacetime perturbs by 10%, well, I better measure the size of my detector with the precision of 10%. Otherwise, I'll never see it, right? So this is the detection side. On the emission side, so this is a key scaling that comes out straight of general relativity, really. The strain is proportional to the mass of the object, the velocity squared, and inversely proportional to the distance. Okay, so let's try to put some numbers in here. So, okay, here are some orders of magnitude that I put together. So, okay, let's consider two cars. Okay, man-made gravitational wave source. So I've got two cars like this, a ton, 10 to the 3 kilos each car. They move at 1,000 kilometers per hour. That's a lot, right? Okay, whatever. I want to round numbers on a 1 kilometer track, right? Okay, whatever. So I'm putting my gravitational wave detector as close as possible, which is one wavelength away from the source. My source is a binary car. I'm putting my detector one wavelength away, which turns out to be more or less the radius of the Earth. Right? So if you put these things together, the typical strain that you get is order 10 to the minus 42. That's completely hopeless, not even in science fiction, right? That's no way, no way. Okay, so astrophysical forces. So now I want binary black holes, and that's what I want to go. Black holes, compared to, say, stars or other things, are extremely compact, meaning they can get very close and go very fast. And that's crucial for us because of this v-squared scale. So you have black holes of 10 times the mass of our sun. It's a typical star mass, right? And these, at the end of their life, black holes their speed is order 10% the speed of light. And that's crucial. I'm putting a black hole 100 megaparsec away, so the next cluster of galaxies. So I'm not even that optimistic in here. We've seen gravitational waves coming from closer than that. So sorry, no, it's a bit optimistic, not even that much. Okay, if you put these numbers together, the typical scaling that you get is 10 to the minus 21. That's still immensely tiny, right? So it means measuring something, so the size of your detector, with a precision of 10 to the minus 21. If you have a detector of a size of 1 kilometer, 10 to the minus 21 kilometer is less than the size of a proton. So that's the kind of scale of the problem, right, that we are facing here. Hide. Okay, yeah, that's what I'll say. No worries. So you're doing your problem sheets in gravitational waves, and you find 10 to the minus 21, and that's you, student, right? So you think, okay, come on, this is hopeless. No way, there's no profit of anything or so. But this is actually the precision of our detectors these days. So that's the scale of the problem. So before going into our detector, let me go into a little bit of the kind of signals that we look for. So the physics here is that you have two black holes that they are orbiting about each other. Now, in Newtonian gravity, the two-body problem is stable, meaning the Earth and the Sun forget about all the other bodies in the solar system, but you pick just two bodies. These things will go on orbiting on elliptic orbits forever, right? So there's a conserved energy and they stay there. So in general relativity, the two-body problem is unstable. because of gravitational waves. So the two bodies are orbiting, they are emitting some gravitational waves. These gravitational waves are taking out energy. Conservation of energy implies that the separation between the two black holes has to decrease. But if it decreases, the black holes will go faster. Faster means they'll emit more waves and so on and so forth. So it's an unstable process, eventually leading to the merger of the two black holes. And then after the merger of the two black holes, you are left with one black hole that's like ringing much like a bell or so. So this is the ringed out phase. So for the gravitational waves that are emitted, they look like this. So this is what we are seeing here is basically two black holes going around each other, going and going. Now the separation is decreasing, so the frequency is increasing. So that's why these cycles here become tighter and tighter and tighter. Then there's a burst, these big cycles here is the actual the merger part. And then this decay here is the final black hole that is ringing out, eventually settling down to an equilibrium configuration at the end. Now, in reality, our problem doesn't really look like this, but it looks like this, right? So these signals are so tiny that the signal that you actually get is this blue thing, right? And the task now is then to find, like a needle in an haystack, like to find a tiny thing into a massive amount of experimental noise, right? So the the detectors to find this thing needs to be big. That's the thing, it's delta L over L. So the bigger your detector, the better it is, right? Now, building big things is also expensive and hard and whatever. So the current experimental facilities have R of kilometer scales. So 4 kilometers is the size of the LIGO detector. So the current facilities are 3 detectors, 2 in the US, 1 in Louisiana, you see here the swarms and so on, 1 in the state of Washington in the US. This site, by the way, is a former nuclear stockpiling site from the war. Then was donated to the physicists. Do your own gravitational waves over there. Nobody wants to leave. The European antenna is actually in central Italy near Pisa, and as you see, we have fields or some over here. So you actually see the things on Google Maps. So they're big. They're big. So the key mechanism. So by the way, I'm a theorist. I do calculations, so I know nothing about the experiments. But these machines are a marvel of engineering, right? So we are talking about, again, 4 kilometer size thing, multiple suspensions, mirrors. These mirrors are like giant thing of like 10 kilos or so on multiple suspension, big vacuum pipes. I think the LIGO vacuum is the longest vacuum chamber, whatever ever done, and the lasers are among the most powerful lasers ever created. So really pushing the engineering side of things. The key mechanism for these detectors instead of a Michelson interferometer. Maybe some of you have heard about this in your classes at some point, but the key idea is that you shoot a laser. Okay, you shoot a laser, then you have a beam splitter, meaning half the photons will go one way, half will go the other way, and these are the 2 arms of the interferometer. So if I go back, these are the 2 arms of the interferometer. So the laser sits here, and then half the laser goes 4 kilometers this way, half the laser goes 4 kilometers that way. Then at the end, at the end of the 4 kilometer thing, the laser got sent back, and the same happens to the other side, and then it goes into a detector down here. Now, if the 2 arms are identical in size, what you get at the end is identical to what you throw in, right? If a gravitational wave goes by and hits the detector and shakes and distorts the space-time a little bit, the interference between these two laser beams when they come back won't be fully constructed. It won't be identical to. So you have a laser beam, it divides. If one of them does a slightly longer optical path, by the time it comes back, you have a dephasing between the 2 laser beams. So you're going to see a dephasing in the photo detector on the other side, right? So that's a key mechanism of how it works. Again, the marvel of engineering is that you have a 4 kilometer size object measured with the precision of about 1,000th or so the size of a single proton, right? So that's a thing. All right. So the LIGO, sorry, I went ahead. So the LIGO detector, they started building it in the 2010s, was approved in 2008-ish, something like this. They started building in the 2010s, and they started getting their first data in in 2015, and it was a remarkable luck to some extent. There's also a pinch of luck in this story, and we shouldn't be ashamed of it. That soon after they started operation, they had a run before at a much reduced sensitivity, but soon after they started operation, they saw this. And this is a Nobel Prize. There's a Nobel Prize in here. So what they saw, so GW, gravitational wave 1509-14, that's 2015, September 14, they saw this. So in the two detectors, so only the US detectors were operating at the time. The European detector was a year, they started taking data a year later or so. So they saw, well, in the Washington side, they saw this signal here. And as you see, this is basically the noise floor. So this is the experimental noise. And then there are these, 4 cycles or so that are big. They are a factor of 2 or so above the noise. And again, here I'm at the 10 to the minus 21 level that I was saying before. And then the other detector saw this. So these are, the red signal is the same, the blue is the one of the other detector. And as you see, here the 2 strains are uncorrelated, the 2 data streams are uncorrelated, and that's because the noise is local. So the noise in Washington and in Louisiana is what it is, what is happening to the ground there. But then these 4 cycles are perfectly lined up. Actually, the reason why you want to build multiple of them is that you never believe a detection with only one, because it's so hard that if you see the detector fluctuates a bit, well, whatever, it could be the postman walking past, right? I mean, they see in this detector, just to say, they see the ocean waves, they see really the postman coming up. I think in Louisiana they had crocodiles, alligators problems, or so. They were, because the beam pipes are in like a half a dome of concrete, and there were alligators hitting the concrete. This is a true story. So anyway, so you want to build multiple detectors to be confident that you're seeing something. So the very fact that they saw 2 things lining up for 4 cycles, that was terrible, terrific, right? So this plot is also crucial for us. So that's the time, that's the frequency of the signal as a function of time, and general relativity as a very strong prediction that this thing here should go at time to the 8/3, and that's what they see. So this slope here is a signal that with the frequency they go as time to the 8/3. That is the crucial prediction that the 2 things are driven by the emission of gravitational waves. Right, so I was actually, I didn't say it before, but in 2015, I was actually doing my PhD here in Cambridge. So I have a Cambridge past, so I did my PhD here almost, when was that? 2015, how many years ago? Too many. Okay, 8 years ago or so. And actually, when they announced the detection from the US, I was in Dept watching the news feed of the detection coming out. And before coming here, I was digging out some pictures out of the time. These are pictures I took at Dept when they were announcing the first detection of gravitational wave. This is Kip Thorne, now Nobel Prize in physics for the discovery of gravitational waves, and there was Stephen in the audience watching the announcements of the gravitational waves being discovered. This is Ulrich Perak, that was still is my PhD supervisor. All right, so the LIGO and Virgo detector are truly an incredible story. So here is what happens. So these are the location in the sky where the gravitational waves are coming from. Now, a gravitational wave detector is not really a telescope, right? You don't point it anywhere. It's much like a microphone that you leave it on and hope to pick up something. So it's very hard, or relatively hard, for us to say where the signal is coming from, right? Much like if you have a microphone, yeah, you have some idea of directionality, but very poorly. So what you can say is that if you have multiple detectors, if a wave hits one detector and then the other, it must be coming from this side or the other way around, right? So this is for the first events where only the LIGO detectors were operational. These are the kind of constraints in the sky that you get. And I mean, if you are an observational astronomer here, that's big. But I don't know how many, maybe thousands of galaxies are in this sky area, right? So this tiny thing, and this guy as well, it's where the third detector, the European antenna, started coming online. And with 3 detectors, you have multiple baselines, so you can triangulate where the signal is coming from way better. So you turn on a new detector and immediately your confidence region shrinks like this. So these were the first, whatever, 6 or 7 events. Just to say, now we are about 100 or so of these. So 100 of these black hole mergers and neutron star mergers that have actually been detected. Now, the next big discovery that happened was in 2017. I call it the gold rush. So what happened in 2017 is the following. That's truly another amazing story. So LIGO sees an event, DW here, that is incredibly loud. So the events that I was showing before, so this discovery or whatever, was a millisecond long, right? This thing is 10 seconds, right? So they saw a thing of like 10 seconds going on, which accumulated signal to noise. So we're extremely confident that it was real, because if you see this 8 Hz power for as long as 10 seconds, it's incredibly strong. But then people got really excited. So already, if you see something long, it means it needs to be light, so the mass needs to be low. So already they figured out it's probably not black holes, because the mass is too low. Then what happened basically immediately is that a gamma ray detector picked up something, right? So the Fermi gamma ray detector, which is an all-sky monitor of the satellite, they picked up something in coincidence. So as soon as the gravitational wave signal, so at this peak, when the gravitational wave that were the largest, the gamma ray detector picked up something. And people at that point got really excited about this. So basically then all the telescopes in the world for that night started pointing towards the location of the gamma ray. And in about 10 hours, because it was that when that sky location became visible from Chile, where most of the telescopes are, in about 10 hours, they actually found something. So if you see these small galaxies at about 40 megaparsecs away, what is it? So yeah, here, I think this was the first one. This source here wasn't there in archival data, and then it is. So this tiny dot here, this tiny guy, it wasn't there before, and now it is. So it was associated, fully compatible, so with being the same source. And this is truly incredible, right? Because that means we are not only observing the universe with gravitational waves, but we are observing the same object with both light and gravity, right? So that's next level. That's next level cool, if that makes sense, right? And then they started follow-up campaigns on all bands of the electromagnetic spectrum and basically found everything. So we were extremely lucky for this event because it was so close, 40 megaparsecs away. It's really close. So it hasn't happened again yet. So this was 2017. But really so merger of 2 neutron stars, because they're too light for being black holes, and also all these counterparts. So these electromagnetic things, they really come because you have neutrons and not just black holes. Was really a gold mine for astronomy for many years. Okay, so but let me move on. The best is yet to come, I want to argue. So we are about here. So this is the size, how many gravitational waves we've seen so far, as a function of how the detectors are going better. So we are about, okay, these predictions are a bit old, but I predicted that in 2021 we had 100 detectors, 100 events, so it was quite right, and something like COVID happened. The detector didn't really improve, or so they got stopped for a week or something. But so if you just get the order of magnitudes here, we are thinking that in about 2 decades, the number of gravitational waves that we observe will go into the millions, right? So we have 100 now. We had 1 in 2015. We have 100 now. We'll have billions in 20 years. So that's a scale of the. We're really opening. We really have the tip of the iceberg right now, and we're really going a little bit down into the bulk of the population. You will need new detectors and a few billion euros, dollars, pounds. It does make a difference at that scale, right? To build the thing, but we're getting there. Okay, so now I'm an astronomer again, so I've seen these gravitational waves, but what do I learn about the astrophysics of the sources, right? And in order to do this, I need one differential equation. So apologies for the non-scientists in the audience, but let me try to go through it slowly. So gravitational waves are dissipating energy and angular momentum. So you have 2 black holes, they orbit each other, they emit energy this way. conservation of energy means that orbit has to shrink, and so on. Now, let's try to ask the question, does it make sense that I see gravitational waves, so that I see mergers of black holes, right? So in other words, is there enough time for two black holes to actually get together? Right. So this calculation was done in the 60s. So this equation here tells you the rate, so this is a derivative, the rate at which the semi-major axis, so the separation between the two black holes, decreases in time. And well, it goes like this. Not even that complicated. Crucially, there's an a to the 3 here. So what I can do, I get this equation here and I'll extract a time scale. So the typical time on which this thing happens. So this is that we call it TGW. That's the typical time on which gravitational wave shrink the orbit. And well, just by dimensional analysis, if I want to get the time, I do A dt dA. And that thing scales as a separation to the 4th power, which is good and bad. It's extremely steep. It's extremely steep power. So that's good because it means that when A is small, so right when we detect the events, so a few orbits, if A is small, T is tiny. So when we detect the events, the entire dynamics is completely driven by gravitational waves. So we can, and we actually do, treat the two black holes in pure vacuum. So in our analysis, where we analyze the data, we assume that the universe contains two black holes and nothing else in the entire universe. And that's an excellent approximation because of this reason, right? Because every disturbance is so useless at small separation, right? Now, the flip side of the same coin, though, is that when A is large, this thing becomes huge, right? So let me turn the argument again. So I'm going to ask, okay, what's the typical separation, AGW, at which the inspiral timescale, so the typical gravitational wave timescale, is equal to 10 to the 10 years. That's the entire lifetime of the universe. So the universe is about 10 to the 10 years old. If you do this thing, you find that this number is about 10 solar radii. Right? So that means if I take two black holes that are more than 10 solar radii apart, they will take more than the life of the life of the universe to merge. Okay? Is that clear? Now it's a problem. Because if you pick two objects, say two stars, their separation is way larger than that. It's like 10 to the 4 solar radii, right? So if I naively pick two stars and hope that they will evolve, to form black holes and whatever, and then merge and explain the LIGO events, there's no hope to do it for real, right? So that's really an interplay between relativity and astrophysics. So what this means is that you need something else that is not gravitational waves at large separation that drives the binaries all the way to something like order of 10 solar radii. And from that point, gravitational waves can take on and lead the merger. So we need a mechanism to dissipate energy, which is of astrophysical nature, not of gravitational nature. You need to shed energy away faster than gravity at large separation. Otherwise, you'll never make it. That's the challenge to actually explain, now that we observe the event, to actually explain that what we observe makes sense. And so there are maybe two ways to do it. And let me try quickly, but you can play with dynamics or you can play with stellar evolution. So if you play with dynamics, so the idea would be that you have two black holes, you have two stars, one star evolves. So black holes are typically the end of the life of stars. So when a star exhausts their fuel, so meaning the hydrogen and eventually the helium and so on, the big stars will end up forming black holes. So you might hope that you get a binary star, this thing becomes a one of the two stars maybe explodes into supernova, or maybe it doesn't, but it becomes a black hole. Then the other star becomes you have a phase with the black hole and a star, and you need to be smart with what you do with the evolution of the stellar evolution in this phase. For instance, you need the phase where the star becomes as big as to engulf the other black hole, so that you dissipate the energy via this engulfing process. This guy will eventually collapse, form a black hole, and that's the event that you see. Or you can have a scenario where these things don't know anything about each other. So these two stars, they're separate, they live separate lives. They collapse, form black holes, and then these two black holes meet. But in order to make this work, you need an environment where collisions are important, where interactions are important. And let me go through this in a bit, tiny bit more detail for the astronomers here. But so in the first scenario, we need something that is called a common envelope. So the idea here is that you have two stars on the main sequence of stars, and then you undergo various phases of mass transfers between the two, including a phase where the envelope of a star, when a star, for those that have done some stellar evolution, at some point stars will expand into supergiants, meaning they become much bigger. If the size of the star becomes as big as the separation between the two objects, then you have a phase where you have the core of a star and the black hole that comes from the other star that orbits in an envelope of hydrogen. And that's actually a mechanism that, if you do the calculation, can dissipate about 3 orders of magnitude in separation. So eventually producing a viable gravitational wave event down the line. Or you can do it in a completely different way. You can do it by dynamics. So the trivial problem in gravitational wave is chaotic, but there's a statistical statement that you can make for which, if you have a binary that encounters another object, the dynamics is very complicated, right? There are many exchanges or so on. One thing flies in, then you see now the yellow, now they exchange, the yellow goes, and then he steals the partner. Now this one is alone, and whatever. It's a whole lot of things. But statistically speaking, the binary that comes in, that goes out, is tighter than the binary that comes in. So statistically speaking, the interloper takes away energy from the binary. Maybe it's not the same guy, maybe they exchanged or whatever, but the binary at the end is tighter than the binary at the beginning. Not in an exact term, but on a statistical fashion. And if you do a calculation, this is some results from, well, semi-recent paper after the first detection. If you do it many times and come up with all the right interactions and so on, you can actually go down and produce viable LIGO events, right? So this is to say that it's highly non-trivial to explain, using viable, plausible astrophysical scenarios, how we get the events that we are observing. All right. So maybe. Okay, I'll skip something here because I want to get to the end. I'll skip this. I'll skip this. Okay, I'll skip all this part. Sorry. I'll go to the next. Sorry, I'll skip a chapter here because I want to finish and then give you time for questions and so on. I think it's important. Right. So gravitational waves is really an adventure at the edge between relativity and astrophysics. And I hope that's the key message here. The facilities that we have are the LIGO detectors that have given us 100 or so of observations, but there's more than that, right? You remember at the beginning, the Andromeda galaxy in different bands of the electromagnetic spectrum. Much like that, there are different bands of the gravitational wave spectrum, right? So what we are observing now stays right here at about 100 Hz in frequency. So we've only observed gravitation waves at a very specific frequency, which is where our detectors are sensitive to. And here we are sensitive to things like the first event, 15 and 14, which are black holes that have the size and the mass, the typical masses of stars, right? Different bands of the electromagnetic spectrum will give you different kind of sources. As you move down in frequency, you typically move up in mass. So for instance, at a millihertz, or right here, you're sensitive to supermassive black holes. So black holes of 10 to the 6, 10 to the 5, 10 to the 6 solar masses that we know populate the center of most galaxies. All the way to nanohertz regime, so 10 to the 9 hertz, where you're actually sensitive to black holes of 10 to the 9 solar masses. So these monsters at the center of the biggest galaxies that we observe, or so on. And different areas of the gravitational wave spectrum require different facilities and different experimental approaches to the problem. So in here at 10 Hz, we have, again, LIGOs on the ground, so 4 kilometer scale things on the ground. And in the millihertz regime, we're going to go to space. And the reason is that the ground is very noisy at a millihertz. So, not really earthquakes, but, micro movements or so on the ground means that at a millihertz, it's basically impossible to take a gravitational wave measurement. So the answer is, let's launch a satellite. But launching a satellite, you're gonna need 3 satellites actually. That's complicated, right? Because you need to send the laser and then get it back somewhere else. So this is gonna be, I'll go into this, but this is gonna be the LISA mission, which is well, I'll say it in a minute. And then, but the key thing is that here to detect millihertz gravitational waves, you don't need 4 kilometers, you need 1 million kilometers, right? And well, 1 million kilometers on the ground is also a bit complicated. So, so the strategy is going to be 3 satellites separated by 1 million kilometers. If you want to detect nanohertz gravitational waves, you don't need 1 million kilometers, you need the size of a galaxy, right? That's even more complicated. And there we do it with an so we don't build the detector, but we use a natural detector, namely pulsars. So pulsars are they're neutron stars that are rotating, and there's a kind of lighthouse effect. So they emit jets of radio waves like this, and every time it's much like a lighthouse, right? Every time the pulse rotates, the jets, sweeps through you in the radio band. So this is basically a radio astronomy problem. The idea being that, so the key thing is that these pulsars are extremely stable clocks. So this rotation is extremely stable, one of the stablest things that exists in nature. So then you can monitor multiple pulsars, and if a gravitational wave goes through, the timing of all these pulsars is correlated because it's the same wave that has gone through. So this is called pulsar timing array, and actually they are really on the verge of a detection. So they basically have it. Let's put it this way. So they basically have it, but they basically have detected. I'm not first person involved into this line of work, but it's extremely exciting. They've basically detected gravitational waves in the nanohertz regime from black holes of 10 to the 9 or so solar masses. I do want to have a slide on LISA though. So we're going to millihertz regime. That's, in my opinion, is going to be the next big gravitational wave revolution. So now the experimental techniques is having 3 satellites separated by 1.5 million kilometers with lasers going across. Now, building a mission like this is immensely complicated. If LIGO was hard, this is even harder. LISA was proposed to the European Space Agencies in the 80s, late 80s or so, and it finally got the go-to last week, something like this. Maybe it was in the news. LISA was in the news last week. That was finally approved by the European Space Agency. So it's going to be built now. So they're sending out actually commissions to the industries and so on. It's going to be a mission led by the European Space Agency with joint 20% contribution by NASA that will detect for the first time gravitational waves from space. And the millihertz sky in gravitational waves is rich. So typical sources that you're going to see. So in this plot here, so this, look at the red one, is the green one is the noise floor. So anything that is above the noise is visible. These tracks here, these big tracks here are mergers of massive black holes, like 10 to the 5, 10 to the 5, 10 to the 6, 10 to the 7 solar massive black holes coming together. All these dots here are white dwarfs, which are kind of compact stars, less compact than a black hole or a neutron star. In our galaxies, that's going to be, in the LISA band. But if you ask me, the most exciting thing will be my dream for LISA are these tracks here. These things that start in LISA and then go away because they might end up in the ground-based detector. So this would be really a dream for me, is to observe the same thing in 2 bands of the gravitational wave spectrum. Right, much like you observed a light both in the infrared and the ultraviolet, something like this, right? So these will be sources. So there's very few of them. Unfortunately, this is a calculation I did, and it doesn't sound that promising. There's very few of these sources, but if they're there, it's going to be super exciting. The idea would be that you have one of these guys that you observe it with LISA in space, and then 10 years later, you see, but so in LISA, you see only the early spiral, and then 10 years later, you see the merger in LIGO. It's going to be amazing. It's going to be like the moon landing. I don't know. In 10 years, 4 months, 24 hours, and 42 seconds, you're going to see a signal at 123 hertz. That's right. If it happens, if it happens, it's amazing. Right, so LISA might have the power to even predict when and where in frequency the merger will happen, LIGO years before. You can even think about tweaking the experiments to make it to see it better and whatever. It's going to be really amazing. And with this, I'm done. Sorry, I skipped point 3. Next time, I'll need to come back to give you the part of the talk I skipped, and that's all from me. Thanks.
Some questions from the audience.
What's the thing you're most excited to figure out with the events that are both from NASA and LIGO? What astrophysics are you most excited to study?
I'm not really excited about the astrophysics, but more about the theory of gravity. So, something I completely didn't talk about, but it's a big thing for us, is to so when with the new observable, there's not only the astrophysics side of things, but there's also the fundamental physics. So one of the key assumptions here is that all this thing is driven by general relativity. And we think that together with quantum mechanics, so general relativity is one of the main pillars of the universe, or our understanding of the universe. Now, these things, and then if you test general relativity on the scale of the solar system or even galactic dynamics or so, it seems all to be true. But we've never tested it, or we are starting now to test it on the scale near the horizons of black holes. These kind of events here, so because there's such a long baseline, you can basically predict where the merger should happen and then check whether it happens there for real or not. And if it doesn't, say if it's a bit earlier or so, it means that you're actually dissipating more waves, more energy than what you think, right? So for instance, there's additional mechanism of energy dissipation that are forbidden in the theory of general relativity. Well, maybe they're not really forbidden, but they're tiny. But with such a long baseline, you can actually, you're very sensitive to these kind of tests. If that makes sense.
Got a question from the Zoom audience.
Sure.
Every time we look at the sky in a different way, we see something unexpected. Has this happened with gravitational waves yet?
Not yet, but I hope it will. Not yet. Part of the reason, it goes back to where is it? No, oh, sorry. Yes. Part of the reason is here. This is part of the reason. And so because the detection problem is so challenging, what you really do, so you need to take out this tiny signal out in a massive amount of noise. So what we really do is that we pre-compute possible signals, and then we basically put it on top of the noise, and if it's a good match, we claim a detection or not. So that means that to some extent, it's not completely true, but to some extent, you kind of need to know what you're looking for in gravitational waves. Unlike, say, a telescope or so, where you look around. So in a telescope where you point at the galaxy or so, we say in a high signal to noise ratio regime, where the signal that you see is much bigger than the noise. So the jitter of the CCD or whatever. In gravitational waves, it's the opposite. We are in a very low signal regime, where we have a ton of noise and a tiny signal, which requires accurate predictions on what you're actually looking for. So the unexpected is there, will be there, hopefully, but it's much harder for us than for conventional astronomy. But yeah, I hope to be seeing a Mickey Mouse event and then spend years writing papers explaining what it is. That would be amazing.
So the least of it, how do you, like, if you need to know the length of things like that, so that's not very tall. I didn't do that.
Well, that's less stringent because the size is a kilometer.
I see.
So, but still 10 to the so it's still what 10 to the minus 21, 10 to the 6 kilometers. So that's still a meter, something like this. Order. It's still immensely hard. Like you need to know the position of two satellites and have two satellites talk to each other with the scale of less than a meter or something like this. It's incredibly hard. I'm glad I'm not an experimentalist working on space missions. It sounds super hard. So I do the data analysis down the line, but yeah, when I hear the experimentalists talking about these things, it's like, what is this? How is it gonna work?
Yeah, so you mentioned that we can measure the precision of 1/1000 of
Yeah.
proton radius and like that. So how can we have like how can this happen? Are we just increasing the frequency of the interval? Or
So I'm being a bit slightly imprecise. What you measure is the relative size of the two arms with that precision. And the idea is to use this microscope interferometer. So you're really sensitive to things that are on the scale of the wavelength of the laser.
For example, simulate multiple times.
Yes. So that's another trick. It's actually why Ray White, one of the Nobel Prizes for the gravitational waves, actually got the Nobel Prize, is to figure out that it's more complicated than this. So it's not just the laser going and then going back. Each arc is what is called a Fabry-Perot cavity, which is basically there's another. So the laser goes in, it bounces, but then there's another mirror, and then each photon has a given probability of going out and a much higher probability of staying in. Each photon bounces in the cavity about 1,000 times before having a decent probability of getting out. So that means that in practice, it's as if light over 1,000 times longer than that. But that's a trick to beat the 10 to the minus 21 limit. So you have an effective interferometer that is much longer than the physical 4 kilometers of the facility. I'm not really an experimentalist, so I'm a bit shaky on these things, but hopefully that's okay. Thanks.
This is from a non-scientific background, so for this.
Absolutely, totally.
The gravitational waves, do they have any mass, and what speed do they travel at, and what sort of dictates the speed they travel at?
That's an excellent question. Mass, yes and no. They have energy, but mass and energy are the same thing. Why? You kind of need to study general relativity for understanding that. The speed is an extremely excellent question. So that's hard-coded again in the theory, in Einstein's theory of general relativity. So it's an extremely clear prediction. You do the calculation, the only velocity that comes out is the speed of light. So gravitational waves in Einstein's theory travel at the speed of light. Whether that's true, well, we want to test it, right? So that becomes then a testing theory perspective where by detecting this thing, you might ask, okay, can I, for instance, if you with a multi-messenger detection, so with this kind of thing, you can ask yourself, right? Well, the gamma ray, I know gamma rays travel at the speed of light. Is that compatible with gravitational waves traveling at the same speed or so on, right? So it's a core prediction of the theory that both gravity and light travel at the same speed, and we call it the speed of light for, I guess, historically. So, but it's the same number. But then it's a thing that we want to test with the observations that we have.
Sorry, I'm just a new relativist. So if this sounds stupid, please forgive me.
No stupid question.
In relativity, we know that for something to reach the event horizon, it takes an infinite amount of time. So it's a little bit strange for me that why do black hole mergers do have an infinite amount of time?
Oh well, okay. So. Okay, the time must get this is a bit it gets to be complicated here, but so there might be a tiny how to explain it. Okay, forget about the black hole merger. Think about just the observer or so on, right? So forget about something. Think about a particle that goes into the black hole, and you have a super duper powerful instrument, whatever that you are seeing it, right? It's black hole merger is conceptually the same, but this is easier to think of. You'll never actually see the particle crossing the event horizon, but you see it getting arbitrarily close. And that's enough for the observation. So what you're actually seeing is, well, the signal of a particle coming arbitrarily close to the event horizon. That's in your reference frame. In the reference frame of the particle, instead, you never even notice it. Nothing is special at the event horizon, right? You just cross it and whatever. So once you're in, then you cannot communicate with the outside.